Hey folks, this is the video to accompany your Lab 1 on relative and absolute time. So this lecture will just involve a discussion of relative time techniques and phenomena, and in the subsequent lab, you'll see that there's also a video on how to calculate an absolute radioactive age date. So we're going to start by reviewing some of the principles of geologic time in regards to relative dating. So here we see a pile of rocks, 4 rocks, labeled 1 through 4, that are oriented from the bottom, which is 1, to the top, which is 4, oriented from oldest to youngest. And this illustrates the principle or the law of superposition, the idea that in an undeformed or not overturned sequence of rocks, the oldest rocks are on the bottom, And you'll see in subsequent labs that there are situations where the rocks are overturned, and we'll see how we figure that out also in later labs. Okay, the second principle we're going to talk about is illustrated here. So we have those same 4 rock layers, but what you see is that there's a V-shaped valley that has cut down in profile through layer 4 and layer 3. So we can see that layer 3, if the river is here, is exposed on both sides of the river, and so is layer 4. And layer 3 we can see underlies the river, but we know that layer 4 used to exist here also, but it has been carved out by river erosion. So this illustrates the principle of lateral continuity. And there's a short video here to help illustrate that. Perhaps. No? Oh, there we go. Sorry. I wasn't patient enough. This is a 3-dimensional model that just kind of shows you that progression. I'm not really sure this adds a whole lot, but again, here you can see the principle of lateral continuity is really only applicable when you have a river that has dissected its way through a rock layer. So again, if you see a picture with a river, especially a canyon, and rocks are exposed on either side, it's typically dealing with the principle of lateral continuity, which is the idea that in this diagram for layer 4 specifically, and for the remainder of layer 3, that layers in the rock were initially continuous and had been subsequently eroded away. All right. Our next principle is going to be illustrated by these 2 diagrams, and what I want you to focus your attention on in both of these diagrams are these inclusions. This is called the law of inclusions, and here's a short video where you can see some field samples illustrating inclusions.
I'm standing next to a volcanic breccia in the Clarno unit of John Day Fossil Beds National Monument in Oregon, and this volcanic breccia nicely illustrates the principle of inclusions, which is a rule that we can use to help us establish the relative age of rocks. The relative age being which one's older, which one's younger. And so if we look at this rock, we can see it has these large clasts or inclusions of other rocks inside of it. Inclusions have to be older than the rock itself that is supporting them, because these clasts had to exist first in order to get incorporated into this volcanic matrix when it was erupted.
So we can see that in our diagram here, where granite, we need to remember from 101, is an igneous rock that comes up from above. So when granite can come up from above and intrude its way into another rock layer, it will melt its way up and through, and slowly that rock layer will become dissolved and not dissolved, but melted and incorporated into the magma. And when that granite cools, sometimes the host rock, in this case it's a sandstone, hasn't completely melted, and that's what we see these chunks of or inclusions of within the granite. Then alternatively, sometimes granite will be exposed at the surface well after it's cooled and all the overlying rock has eroded away. When that happens, chunks of the eroded granite can become incorporated into the bottom of the sedimentary rock that overlies it, that forms afterwards. Sometimes people call the bottom of a rock layer the basal portion of the rock layer. Basal just kind of means bottom. And so because sedimentary rocks form when chunks of pre-existing rocks get cemented together, the chunks of the pre-existing granite can just become grains, large grains certainly, but grains nevertheless within the overlying sandstone. They are included or inclusions within the sandstone. And sandstone is very often illustrated with a stipple pattern. Granite and other igneous rocks is kind of illustrated with this random pattern that is supposed to illustrate just sort of crystallization, but with crystallization without any sort of orientation. So to the back the law of inclusions, in both of these situations, the inclusions are older than the rock that contains the inclusions. So that's important, and you'll be looking at some photos of that. The next law of relative dating is called the principle of cross-cutting relations, and this is something that you likely remember from 101. It talks about two different types of features. When we're looking at the principle of cross-cutting relations, we're talking about igneous intrusions, and we're also talking about faults. And so what you can see here is one big fault labeled 2 here, and you can see that fault 2 cuts all through layer 1 here. So that means that in order for the fault to break these rocks, the rocks had to be older. So therefore, the younger feature, the fault, cut across the older feature, which are all these rocks. So then you see also probably notice this igneous intrusion. This is the other symbol that people often use for igneous rocks. And you can see that there's an igneous dike, which is a body of rock that kind of cuts across or intrudes through pre-existing rock layers that are sort of in opposite direction to their to the orientation of the host rock or the sedimentary rocks in this case. So igneous intrusions come up from below in part of the Earth's sort of like lower crust sometimes, and will melt its way through that material. But it can only melt its way through material that's already there. So the younger feature, once again, which is the igneous intrusion, cuts across the older feature, which is the pre-existing rock layers. Rock record can be lost in what's called an unconformity. An unconformity is also important whenever geologists want to tell a story because it's a gap in a rock record. Typically this is due to erosion. It can also occur because there's a period of non-deposition also. To illustrate unconformities, here we're looking at a cross-section of the Grand Canyon from the basal portion of the Grand Canyon where the Colorado River cuts through the Vishnu schist, all the way up to the upper rim of the Grand Canyon with the Kaibab Plateau. And you can see that the rocks of the Grand Canyon range from Precambrian in age all the way to Permian in age. And Precambrian is a term that's often used for anything that is older than about 540 million years. So all of the red lines here illustrate different types of unconformities. We're going to start by talking about this unconformity here. Does anyone remember? Do you remember from 101 what this is called? There's 3 types of unconformities. This one is an angular unconformity. We're going to watch a short video about how angular unconformities form and then pop back to this slideshow. So angular unconformities form when you have a series of sedimentary rock layers that are deposited. Typically this is done when sea level is high, and then sea level falls. When sea level falls, and especially when rocks are uplifted, you can see that they're tilted. And when they're tilted, you start to have erosion at the highest elevations. And as that continues, you have leveling of the ground surface. And this is where we've lost all the rock layers, right, that used to overlie this erosional surface here. Then as we go through time, sea level will rise. And as sea level rises, once again, you have sedimentary rocks that are originally deposited horizontally. That's also called the principle of original horizontality. And your angular unconformity is this erosional surface here that marks where you have tilted rocks overlain by flat-lying rocks. So your second type of unconformity is illustrated here between the Moab limestone and the Redwall limestone. And in fact, there's another disconformity between the Redwall limestone and the Supai group. These are all sedimentary rocks, right? Limestone is sedimentary, and the Supai group is actually a series of shales and sandstones. A disconformity is created when you have, I'm going to talk you through this, when you have erosion between flat-lying layers of sedimentary rock. So this diagram is a little confusing. What you're going to see at first are a series of rock layers that are deposited. Okay, and so this is the rock layer. This is the complete rock record. All of these funny little symbols here illustrate the presence of certain fossils. So there's not going to be erosion in this left portion, but there is going to be erosion in this right portion about halfway through. And the reason there might be erosion is because part of it might be above sea level or very close to sea level. There might be no deposition of some of the layers here on the right because maybe they're very close to the source area and again, it's above sea level, or maybe a river gets diverted and so sediment is not coming into this area but is still coming into this area. But whether it is erosion or non-deposition, what will happen is, oops, let's just pause it there, is you see that not all rock layers are represented here. So you have the first 3 rock layers on the left, you have the same 3 on the right, and then you can see that this whole section of, let's see, 1, 2, 3, 4 rock layers are present in the left and they're not present in the right, and that's because they were eroded away. They used to be here, they were eroded away. And using fossils, we can recognize that there is a big gap in geologic time there. Fossils are great for recognizing disconformities. A lot of times there'll be mineral deposits as disconformities as well that will give us a clue that there's been some erosion. Because to the casual observer looking at some flat-lying rock layers here, it doesn't look like there's been a whole lot of erosion. So that's the second type of unconformity. There's angular unconformities, disconformities, and then nonconformities are present here between the igneous Zoroaster granite and Vishnu schist, which is metamorphic, and the sedimentary rock layers of the Unkar group. So here's the nonconformity. And real quick, I'm going to go back to the first animation, which had the link to that. Or didn't. I closed it. Sorry. I'll skip ahead. Okay. All right. So nonconformity occurs when, in this case, it could be igneous rock or metamorphic rock gets exposed at the surface. Now we know intrusive igneous rock and metamorphic rock don't really form at the surface of the earth. So in order for them to be exposed, there has to be weathering of overlying rock layers. And then you can have a period where sea level rises and you can see that there's the deposition of sedimentary rocks on top of igneous rocks in this case. And you can also see that the principle of inclusion is at work here because chunks of this igneous rock have been incorporated into the basal units of the sedimentary rocks. So if we go back here, the Vishnu schist and the Zoroaster granite never formed at the surface. Schist is a intermediate grade metamorphic rock and granite is an intrusive igneous rock. So the only way they can be exposed at the surface is if there was initially erosion of all overlying rock layers so that you could have deposition of the Unkar group. You can also see that the Unkar group has been tilted due to tectonic uplift at a later time. So that's exciting. So that includes all of the information that you need to do part 1 of the lab. There's another video before you start part 2 on absolute time.